So now if we come back to our picture, let us add another object. And this object, it's not going to be a it's not going to be another spring. In this case, it's going to be an object we call a damper. And a damper is drawn in the following manner, although it has many different representations. And let's give it a coefficient gamma. You can also give it a coefficient b. You can call the coefficient smiley face. You can draw a happy little smiley face and let that be your damping coefficient. But we're going to use gamma for gamma's sake. So the same way that the spring provides a restorative force back towards equilibrium, what a damping element does is it provides what's called a damping force. Now, if you were to imagine the word damping, it's not something that necessarily depends on where you are, but it kind of acts on how you move. For example, if you're moving through honey, it doesn't really matter if you're 50 feet into the honey or 2 feet into the honey, you're going to be moving slower. And in fact, the faster you're moving through the honey, the harder the honey is pushing back against you and slowing you down. So this can kind of naturally lead to the damping force being equal to the negative of some constant multiple of your velocity. Let's rewrite that v so it's legible, of your velocity. Again, how do we interpret this? The faster you're moving in one direction, the harder the damper is providing a force in the other direction to slow you down. So one common system we have, and the origin of this image, is what's called a dashpot damper, where you have, well, let's not draw it sideways, where you have fins on a stick. You can imagine it like this. Maybe these have some perforations in them. And you have water, right? So let's draw some nice water, and let's fill it in right here. So you could imagine that moving this stick up and down, the faster you move it, the more the water is going to be pushing against you, right? But if you move it slowly for 500 feet, it doesn't make a difference if you've been moving it for 10 feet, 500 feet, 10 million feet. It just matters how fast you're moving it, how hard it's pushing back. So that's how we get to this equation naturally, and then the gamma term depends on the specific damper we have. But that's not of importance right now. That is an element of the problem. So now, in our new equation, we are accounting for not only a spring, but a damper, so this is not necessarily going to oscillate forever. In fact, we know from observation that it can do one of three things. Generally, if you have a mass oscillating on a spring, if you've ever played with a spring and a mass, or a pendulum perhaps, you know that because of air friction and ground friction and whatever other imperfections, if we call this the motion, let me draw that in black, and we call this time, it's going to do one of three things. So this case in blue is called underdamped, where it kind of just swings back and forth, almost like if you follow, it's going to go like this, this, this. It's going to slowly slow down, but it's never actually stopping, or in real life it does stop, but mathematically it doesn't. It kind of just wiggles back and forth. Then there's the other case, which I call the extreme honey molasses case. But the proper term is overdamped, where it will begin to move, but it does not have enough energy, or the coefficient of damping is far too high for it to ever oscillate. So it moves and then slows down to a halt. There's a final case, depending on the coefficients, where it has enough energy and the damping coefficient is right for it to cross precisely once and not anymore, right? So you see, I'm drawing them coming towards the zero line, but in theory, at least the red and orange cases, as they go to infinity, they approach zero, but mathematically they never actually go to zero. Or rather, they never actually reach zero. It's a limiting case. Whereas the underdamped case is always passing above and below zero, or in this case, behind and forward to equilibrium. So blue, underdamped, red, overdamped, orange, critically damped. Right? So with these three options in mind, now that we have an intuitive understanding of our system, so let's actually model this in the same way that we modeled our previous mass spring damper system. So we have, again, the sum of all forces is equal to the mass, and we know acceleration is the second time derivative. From this, we can incorporate not only the damping force, but also the spring force. So let's write this back down. And remember, v is actually the same thing as the first time derivative of position. So we can write out this equation, and you can show as an exercise that this directly leads to the following equation: m x double dot plus gamma x dot plus k x equals to 0. So plug in these two, because remember the forces acting on the mass is this plus this. Remember they're both negative, and it's equal to mx double dot. And then simplify, or rather rearrange, and you should get this. You may do that as an exercise if you like. So along with the simplification we did last time, there is a simplification we can do here, but let's explore the solution so we can arrive at it. So let's divide by m again. So we'll get x double dot plus omega over m x dot plus, and let's just go straight to omega naught over k, omega naught squared x equals 0. Now we already know that this is going to end up being solved via a characteristic or auxiliary equation. So we can just skip the formalities, and we can get straight to solving it. So we have that minus gamma over m plus or minus the square root of gamma over m squared let's get this under square root minus 4 times 1 times omega naught squared all over 2 is going to be our R1 and our R2 for our differential equation. Now, I argue that instead of having this term right here, it would be nice to first of all get rid of this 2 and this 4. So why don't I have a new term? Let's call this lambda. Lambda, where it's equal to gamma over m, right? But we also give it a factor of 2. Now let's observe what this would do. It would take this gamma over m and make it negative 2, which would cancel out with this. But we also have to worry about this case, where this would become 2 lambda squared, which is 4 lambda squared minus 4 omega naught squared. And the 4's factor out, and then when you take the square root, you can simplify the 2. So let's instead rewrite our differential equation, knowing what we know about the amazing implications of using 2 lambda instead. 2 lambda x dot plus omega naught squared. X is equal to 0. Now we know our two r's are going to be of the form minus this, minus 2 lambda, plus or minus the square root of 4 lambda squared, minus 4 omega naught squared. Take the square root of that, all over 2. Now, what do we notice? These 4's factor and come out, cancels out with this 2 as well as this 2. So really, we get that R1 and R2 are equal to negative lambda plus or minus the square root of lambda squared minus omega naught squared. This is a very important equation for our situation. Why? It's because we can actually predict the behavior of our damped system based on this term, right? Why is that? Let's take a second to think, what determines if our system, or rather our motion, is oscillatory or not? Remember from the previous example, if we take a look right over here, what caused these sinusoids and cosines to appear is this I term. And this I term occurs when the value under the square root is negative, right? If that was positive, there's no way an I is getting under there, right? Unless it began complex, but we don't worry about that case. So what we know about this is that it's not going to have a complex term, or rather, it's not going to be a complex root if this is greater than 0. So conversely, we know this will only be a complex root if this under here, called the determinant, if you remember from quadratic terms, the determinant is less than 0. So if we do lambda squared, let's call our determinant d right here, lambda squared minus omega naught squared. If our determinant d, it has 3 options, if we recall from a quadratic. Right? If our determinant d is less than 0, then this number is going to be complex, which means our solution is going to have some sines and cosines in it, which means it's going to be oscillating up and down like this. Now notice, it's going to have a constant term out here at the front. If we take a look at e to the a plus bi, what we really get is e to the a times e to the bi. We know e to the bi expands to cosine theta plus I sine theta, so e to the a is just a real number multiple, or a real number scalar, of those cosine and sine functions of that wave. So we know that this number is just going to be like a sine and cosine with a coefficient out the front, which depends on x. So in reality, it's going to be a sine and cosine decaying over time. So this leads us to believe that this is going to be the underdamped case. So what we have remaining is those 2 cases I talked about previously, the overdamped and the critically damped. Now, it's quite clear that if the discriminant is positive, that this number is just going to be another positive number, so we're just going to have 2 distinct roots. And we know that if we have 2 decaying exponentials, they're just going to compete in the beginning, and then one of them's just kind of going to win, and it's just going to go down, right? And keep in mind, this is 0, this is, this is x, this is y. There's going to be some competition in the beginning. This is like the mass going away from the wall, but then it's kind of just going to come back, and it's never going to cross. So we can say that this case where it's greater than 0 is going to be the overdamped case, which of course leads the 0 case to be critically damped. And if we look, if this is equal to 0, this is just going to be minus lambda, which means it's just going to be the same root twice. Now we know what to do if we look at our solution. We know what to do if it's 2 distinct values. We just put in the first value, add the second value, constant multiples of both, c1, c2. And we know what to do if it's complex. But what do we do if it's repeated values? Well, there is a method by which you can find another solution based on a given solution, yp. So if I have a solution to a differential equation, now let me write this different so it's not like gamma, yp, then by the method of reduction of parameters, I can find another particular solution, yp2, let's call this yp1, where this will also solve the differential equation I'm looking for. In this case also, as you have proven in class, the sum of these 2 will also solve the differential equation. Now, you may or may not have been required to do this or have been shown in class, but it turns out that if you have a solution of e to the rx as your particular solution, for example, if we find one repeated root, or the first root of the repeated root, then via the method of reduction of parameters, we show that x e to the rx is also a solution. And you know what? If we had 3 repeated roots, we could extend this and say x squared e to the rx is also a solution. And this goes on infinitely. You can have 50 repeated roots, and you'll just keep adding x, and it will be true. It will still be a solution. Just make sure that these roots are actually repeated and that they are the same. Remember, plus and minus are distinct.